We're going to continue looking at exponential functions, and this time we're going to focus more on applications. And remember, we already considered the basic look of an exponential function in the form fx equals avx. Remember, this is a vertical stretch. It's number in front a, or compression, depending on the value of a, greater than 1 or less than 1. And the other look that doesn't have a being equal to 1 is just this. Okay, so you have these two basic looks, but again, there is a 1 in front here. That a is a 1 when we write that. And we know that if, again, b is greater than 0 in an exponential function, the function is always increasing. So again, just a quick reminder, while if b is between the function is always decreasing. And again, I'm making the assumption when I'm saying this, that if I'm looking at this model, the a is greater than 0, positive. Because again, if a becomes negative, remember we flip across the x-axis and we get something entirely different. So if b is greater than 1 in application, we call b the base of the exponential, and then so the b part is going to now be called the growth factor. So yes, it's something you have to remember these vocabulary. Now, if b is between 0 and 1 in applications, we call b the decay factor. Okay. From now on, I want you to think of the base b as being composed of the following. So the b can be broken down into 1 plus r. Okay. Where a, sorry, I'm not quite sure a, it's where r is called the growth rate if r is greater than 0, or decay rate if r is less than 0. So r, again, so there's a lot of things going on here, the b, the r, the a, but you have to kind of understand each one. So please spend time kind of understanding this. Again, if this r now is the growth rate, if again r is greater than 0, decay rate if r is less than 0. But we'll make sense of this so it kind of sticks in your mind. So the familiar function, again, that we wrote, fx equals abx, in application should be viewed as, and we're also going to change this again later when we add another component. Okay. So instead of writing b, we can think of it as 1 plus r, which starts to break this down even further. Now, what does the 1 mean? This means, this is taking into account, as you'll see in this example, original amount. So that's what it's accounting for. It's just original amount. Well, this is going to signify the either increase from the original or decrease from the original. So let's see how this works. The population in a small town is growing by 5%. If the town currently has 500 people, write a function describing the population t years after it had 500 people. So let's kind of start with creating a nice little table here. Okay. And I'm going to call this t for time, since that's the variable. So instead of using x, I'm going to use t. And on this side, I'm going to enter f of t. Okay, so what's happening? Well, at 0, meaning right at the beginning, I have 500 people. Okay. And it's growing by yearly, so I have to look at the unit, yearly by 5%. So now this must mean that t here is in years. That's the unit. The output unit here is people. So what happens a year later? Well, it says that it's growing yearly by 5%. So what happens is that we're going to have to take 500 and multiply that by 0.05, 5%. And what happens when I do that? Well, Again, what this function is going to give me is the population size, T is after it's 500 people. So it's increasing by 5%. So I take 5% of 500, but what do I do afterwards? Then I take this result, which is the increase, and add 500 to it. So when I do that, 5% of 500, on the calculator, it should be 25, right? And then add that to the 500, and that gives me 525. Okay. Now, before I continue, I'm going to do one more thing. So this is where, again, algebra comes in. We can start deciphering things. Notice that I can take 500 here, and I'm going to keep this equal sign. I'm going to write it below since this is equivalent to the statement. And what I'm about to write is equivalent to the statement. This is just adding these two. If I notice I got 500 here, 500 here, I can factor out 500. Okay, now I'm going to reverse things a little bit. I should have probably started with the 500 over here. But when I factor out 500, what do I get? Well, if I just concentrate it for a minute, there's a 1. 500 times 1 is 500. Again, I'm reversing these two, composing them. And on the other side, I get a factor of 500 out of here. I get 0.05. So I'm going to write parentheses because I factor. Notice again, if I distribute 500 times 1, 500, 500 times this, that's expression. So all of a sudden, this 525 is coming from what? 1 plus 0.05 is 0.05. Notice there is your 1 and your R. What is the 1 doing? Well, the 1 is accounting for this initial amount that I'm going to add the increase to. That's where it's coming from. When I put it all together, actually add the 1 up, what do I get? It's a 105. And what is this 105? That's the B. And in this case, since R is greater than 0, this B right here is your growth factor. What is this 5%? Well, the 5% is the R. So this must be, and it's greater than 0. So this must be your growth rate, since again, R equals 0.05 and R is greater than 0. Okay. So what happens year 2? Okay, so year 2, I take this 525 and repeat. So it's going to be again 525, and to add 525, I'm going to add 5% of that 525. So now, again, we can just look at it from this perspective, take out the 525. So again, I just want to emphasize what we're doing here. And what I have is 1 plus 0.05, which again gives me the same response, 525, 1.05. So notice all I'm doing is multiplying again by 1.05, which really all I'm doing is multiplying by the B. Okay. So if I were to follow this from beginning to, so I just did 0, 1, and 2, but if I were to just generalize this, what's happening? Well, where did the 525 come from? The 525 came from this right here. That's where the 525. So if I start from the beginning, so I want to construct the whole thing. When t equals 2, what happened? Well, I had to go to 0, 1, and then get to 2. But when I got to 1, what happened was I had 500 times 1.05. And then that gave me the 525. When I go to 2, what I'm doing, I'm taking this 522 and doing it again. So I'm multiplying each time by 1.105. So really, to get to 2, what am I doing? I'm getting 500 times 1.05 squared. And so that's really the structure of this. So to write a function describing population T years, really what I have is this. T is the number of years. I start with my initial start at 0, and then, because I'm increasing by 5%, I'm just going 1.05 t. So if I want to know what it is 3 years down the line, then I'll put it 3 here, 5 years, 5, and so on. So I'm increasing each time by 5%, but the result is multiplying by this 1.05, and the 1 is accounting for, what's the 1 accounting for? The previous amount that I did. So not from the beginning, but every time you do this, it says, okay, what was the previous initial? So as far as the 1's concerned, for when I get to 2, this is now my initial. But instead of having to go through this process of 0, 1, 2, 3, 4, maybe go 5 iterations to get to the number 5, I just do it on one shot, and there's my function.